Okay, we will get started here with our first full-blown lab. Hopefully you've submitted everything needed for week 2. I'll take a look at it later this afternoon. This is kind of the flow for today's lab, and this is kind of what I followed for Monday, and it seemed to work okay. So we have 2 experiments we want to look at. One is UV-Vis, the other is Diels-Alder. We will start with the Diels-Alder pre-lab PowerPoint. I put together this PowerPoint keeping in mind your lab report assignment, which is 100 points. We'll go into lab flow and look at that as well. I'll tell you how that works. Then we will go into UV-Vis spectroscopy PowerPoint. I'll give you a pre-lab of that. And that's keeping in mind these 2 lab assignments, the food dyes, which we will look at together. And then we'll also look at this one. The Job video and the extra credit, I'm going to let you do that on your own. Then Spartans, lesson 1 and 2, we'll take a look at it. I've already recorded the instructions, and that seems to work pretty well with Monday, at least those who attempted it. I won't say the entire class has done it, but those who attempted it didn't have any issue. So some of them have contacted me. So let's try this and see. If this just doesn't work, then, I can look at a different teaching methodology, but we'll start here. Okay, so what I'm going to do is start with the Diels-Alder PowerPoint, the PowerPoint put together, keeping this particular lab in mind. So let's get started with that. That's this PowerPoint here. The recording is going on, so I'll try to write detailed notes for you guys. Everything on this PowerPoint will be very useful for you to answer your post-lab, which is in lab flow, okay? So let's get started with this. The theory is very minimum here. We have covered pretty much everything in the lectures. You can always go back to that. This PowerPoint is going to focus on the experiment and the experimental aspect of today's, lab. So this is all that you have for the theory. A Diels-Alder reaction is a cycloaddition reaction. What that means is it's an addition reaction. 2 different things are going to get added, and it's going to lead to the formation of a ring. And the ring is very specific. It will always lead to the formation of a 6-membered ring. If you can't hear me or you see a lag, please let me know, because there is no lag on my side. And my AirPods are indicating that everything is fine. I sometimes just keep writing and I forget. So I hope someone will unmute and let me know. So the cycloaddition will lead to the formation of a 6-membered ring. This numbering is another famous thing we've been doing for a while. 1, 2, 3, 4, 5, 6. And you're going to involve 4 pi electrons from the diene, 2 pi electrons from the dienophile. So this is called a 4 + 2 pi cycloaddition reaction. Leads to the formation of a 6-membered ring, a new pi bond between 2 and 3, 2 new sigma bonds between 1 and 6, and 4 and 5. So those are the major changes. The reaction is concerted, which means it's a 1-step reaction, no intermediates, only transition state. The arrows don't have significance. In general, the reaction is considered non-polar. However, if you look at the literature in detail, you'll find that something like water do accelerate the reaction. So there is some polarity to the transition state itself. So that's a little bit for the theory, you know, a lot more. Let's look at today's reaction. Today's reaction in lab flow, you have a detailed procedures between anthracene and maleic anhydride. Anthracene has 3 benzene rings fused to each other. So this is called a polycyclic aromatic hydrocarbon. You can see the extended conjugation in anthracene. Right? You can just get these moving throughout the ring. And I'm going to erase those, but the point I want to make here is you have extensive conjugation. So this actually moves from UV light to visible. Anthracene is actually a bright yellow solid. So that's another part of the lab today that we are going to study. So you have more conjugation, lower the energy, higher the lambda max. It'll move from ultraviolet to visible, which means those compounds will be brightly colored. This one is a yellow solid. Now, in today's context, what I want to point out is here's your diene that reacts. So this is your 1, 2, 3, 4. This is your 5, 6. This is your dienophile. The dienophile is a maleic anhydride. All right. Now, the Diels-Alder reaction is a very efficient reaction if the dienophile contains electron withdrawing groups. And here are 2 electron withdrawing groups. So electron withdrawing groups are those that will pull the electrons. So let's go ahead and see how that's electron withdrawing. So you see how I kind of overextended that. You see how it goes on both sides. So the double bond O can pull the electrons towards it. So you can see that you can get a resonance structure that looks like this. And similarly, on the other side, this double bond O can also be O minus. Okay, so you have a dienophile that's very reactive because simply because you got 2 electron withdrawing groups, top and bottom here. Xylene is a solvent that is used. So just to give you an idea of xylene, this is benzene. This is toluene. That's a benzene with a methyl group. The second methyl group can go 1, 2, 1, 3, 1, 6 positions. That means the 2 methyls can be next to each other. That's 1, 2. They can skip a position 1, 3, or they can go exactly opposite. I'm sorry, that's 1, 4. These are called xylenes. So when you have 2 methyl groups, they're called xylenes. You can have 1, 2, 1, 3, and 1, 4 xylenes. The reason I wanted to explain that is you can see the plural there. So it's not just one compound, it's a mix of these 3 xylenes there. You're going to reflux it 30 minutes. The advantage of using xylene is it's not toxic like benzene. Benzene is carcinogenic, and toluene is also not toxic. So we could have used toluene, but the advantage of xylene is it has a very high boiling point. This is a high boiling point reaction. Cycloaddition takes place, and you can see that I'm going to give the numbers here. This is going to be 1, 2. So the double bond is between 2 and 3. We've always been seeing that. And then a new bond is between 1 and 6 and 4 and 5. And there is your Diels-Alder reaction. The name itself is not important, but I've given it there. Now, if you're wondering why these compounds are so important, they have a lot of use in the medicinal field. As you can see, some of the common applications of these kind of structures. Diels-Alder reaction is a Nobel Prize winning reaction because you can make such kind of architecture just in one shot with no waste produced. In the lab, we do a similar reaction, but we do it in a greener way. So I just wanted to point that out to you. We do not use anthracene, we use cyclopentadiene. So that's our cyclopentadiene. We use the same maleic anhydride, which is a white solid. Our reaction is simple and straightforward. The advantage of this reaction is that you can just do it at room temperature. If you want to warm up the reaction, the most you go is 40 degrees Celsius. With xylenes, you're going to hit a very high temperature. So this is a much greener modification of that existing reaction. The reaction only takes approximately 10 minutes at the most. This takes 30 minutes. Excuse me, at reflux. So you got to get it to reflux, which may take 15 to 20 minutes. And then you have to reflux it at 30 minutes. This one, just light warming, 10 minutes, the reaction is done. So this is a greener modification. For those of you who are wondering what reflux means boiling, at the solvent's boiling point. So the temperature can never go higher than the solvent's boiling point. That's the most it will be. That's called reflux. So it's a very smart way of controlling temperature. You don't have to put a thermometer inside your flask to check what the thermometer, what's the temperature going to be. The temperature, the most it's going to be is the boiling point of the solvent. It's not going to go higher than that. That process is called reflux, and it's used a lot in organic chemistry labs. This is another way to draw the product. And I like this way because it points out the stereochemistry, which is not drawn very nicely here. But what we are doing here is, again, we are using the middle ring, but we can draw this a little bit differently. So this 6-membered ring that we have, 1, 2, 3, 4, 5, 6. So I'm going to show you how this is drawn. You know, after the reaction, you can always draw that 1, 2, 3, 4, 6 ring this way. So this will be your 1, 2, 3, 4. Your double bond will be here. And then this is your 5 and this is your 6. So if you go back to the structure, you should be able to see that comparison. Then at 2 and 3, you have this benzene ring coming through. So we're going to draw that. Okay, that's important. And then at 1 and 4, if you see at 1 and 4, you got this benzene ring connected. So I'm going to raise this up and draw that benzene ring there. Now this ring right here, I'm going to draw it down, and this is the advantage. You can show the endo product very nicely. So I'm going to draw the 5 and 6 inside. So what I want to do is draw it straight down. See, this really shows the endo nature of the product. Only the endo product will be formed. Exo is not formed. This is called the Alder rule. You know this from theory. So this method is nice. I just think this is not really showing endo, it's showing flat. What you want to do is really get these bonds moving down. Kind of exaggerated even. That really shows that this particular group, you know, is very close to this newly formed double bond, which is 2, 3. All right. So that's a reaction we're going to be studying today. And just a little bit of, you know, the schematic itself. You're asked to draw the reaction. You may draw it this way, or you may draw it this way. You can draw it, take a picture, and upload it. But if you draw it this way, try to show the endo. You know, it just makes more sense. Now, this information that I have on the next slide will be very useful for you to calculate percent yield and theoretical yield. The 3 chemicals that I used today, anthracene, maleic, and hydride, I have the chemical formulas, melting points. You don't need that for yield, but it's good information. Molar mass, and then we have xylenes, the molar mass, the density. So you're asked to calculate percent yield, and I have a sample calculation here, which should help you. I'm just saying that if I started with so much anthracene and so much maleic and hydride, what's a theoretical yield? In order to calculate the theoretical yield, what you need to get is the limiting reactant. In order to find the limiting reactant, you have to start with the amount of anthracene that you're given and get the amount of the product that will be formed from anthracene. Then you have to start with the amount of maleic and hydride given and get the amount of the product that's formed. The one with the least theoretical yield, the corresponding chemical will be your limiting reactant. In my calculation, it turns out to be maleic and hydride. This is a sample calculation, so you will be doing with the numbers that you're given. So let's go here. Let's go to lab flow. I'm already opened in this. This is where you and I should be. I didn't want to start from the beginning because for some odd reason, before I get to the report, it shows everyone's grades, and I didn't want that on the screen. So this is where you should be. You know, and then what you're going to do is, are you completing? So this is the lab report. This is data and report submission. This is not your pre-lab. Your pre-lab should be all done. Okay, so you're going to choose yes. Okay, because you're completing this experiment online, then you click next. Then request for provisional data. Then confirm. Then you get all your data here. See the amount of maleic and hydride in my calculation, I took 0.505, but here it's a little bit different, right? A lot different. Anthracene, mine was 1.012. This is 0.102. Your crude product, you know, this is the actual yield is given. So you will calculate the theoretical yield, use this actual yield to calculate percent yield. But hold on, you're also given the recrystallized product. So the recrystallized product is your really pure product. So you want to use your recrystallized product for calculating percent yield. And all of that, you're going to put it in here. Okay, that's a big bulk of the lab. I think that's 24 points. So with this sample calculation, you should have no problems. Moving along, I've given you the molar masses as well. So it's a simple direct calculation that you want to go with. All right. Any questions on that section, just this section, starting from use the data above all the way to percent recovery from the recrystallization? You're also asked percent yield from the crude. So you're going to use both. You're going to use the crude as well as the recrystallized, okay? All right, so the second part of your lab report deals with IR spectrum. So I'm going to be writing stuff on this, but it turns out they want you to comment, Lab Flow wants you to comment on the IR spectrum, but doesn't give you the IRs of anything. So I've given you the IRs from open sources, resources, SDBS, which is a Japanese database. I've given you the link because it's kind of useful. It gives you the IRs and NMRs and carbon 13s, just mass spec of most of the known compounds. This is maleic anhydride. So an anhydride, yes, please.
I'm sorry. Did you say, I thought I heard you say something about pre-lab. All we had to do was the pre-lab quiz.
Correct.
And read over, right?
Correct. So what I just showed you now, is the lab report. It's not the pre-lab.
Okay, but we weren't supposed to submit anything other than the quiz?
The pre-lab is the only thing that you should have submitted.
And that was
pre-lab, that was a quiz, yeah. The
okay.
Pre-lab, okay, you should have submitted the pre-lab for Diels-Alder via LabFlow, and that's the only thing that's required for today.
Okay, and that was the quiz. Okay, I just want to make sure I didn't miss something. Thank you.
No, that is the only thing. Your Canvas should clearly give you the deadlines. Hopefully it is. So all of this stuff that I'm showing you is only due next Monday.
Okay, thank you.
So everything I explained so far until the sample calculation of the theoretical yield will take care of the first question in your lab report, Diels-Alder reaction. The second big question is the IR spectrum, and I think that's like 25 points, but the IR spectra are not given, and you need this information, and I'll tell you where you can upload this. So I want to start off with the structure of the anhydride. This is your structure of the anhydride, and you can't miss that here in the maleic anhydride. Okay, right there it is. Now the anhydrides, you're basically hitting it with infrared. Okay, so the polar bonds will absorb the radiation, they will stretch. When they stretch, they undergo a change in dipole moment. When they undergo a change in dipole moment, the detector will detect that change and will read out a graph for you like this, okay? Now, your big polar bonds here, there are two of them, the carbonyl, C double bond O, and the single bonded carbon-oxygen bond. Now, when the carbonyls absorb the infrared radiation, the bonds can stretch in the same direction. You studied this last semester. This is called symmetric stretching. Now, the bonds can stretch in opposite direction. What that means is one bond can stretch like this, the other bond stretches in the opposite direction. This is called asymmetric stretching. So this is how the carbonyls will respond. So you will see two peaks for the carbonyl, but it turns out that maleic anhydride is very hygroscopic. So can someone tell me what is meant by this term, hygroscopic? What does that mean? Anyone? It absorbs water, okay? So it'll absorb water. It's quite polar, absorbs water quite easily. So you don't get two very nice sharp peaks, but this is where you get it, okay? That is your maleic anhydride, and that's where you see your broad peak. So if you really look at it carefully, you should see this is probably 1600, 1700, 1800, 1900. So you're seeing a peak approximately 1900 with numbers, kind of close to that. And then a broad peak that kind of goes from 1800 to 1700. So those are all, your anhydrite peaks, broader than usual. I'll show you some short peaks, broader than usual. You just can't help it. Maleic anhydrite tends to absorb water as you run the IR. Now we got another bond. That's your carbon-oxygen bond, all right? Now the carbon-oxygen bond will come in the fingerprint region. And that's usually around 1100 wave numbers. So right here is your carbon-oxygen bond. So that's your carbon-oxygen stretch. That's the way the bond is going to stretch. And these here are your C double bond O stretches. So the bands you see here are because of the way the carbonyl stretches, symmetric and asymmetric. That CO stretch comes in the fingerprint region. So you're asked to compare and explain the IR spectrum. This is going to be one band you're going to explain. This is going to be two that you're going to explain. Then we got the IR spectrum of anthracene. A quick look at anthracene tells you that it is a hydrocarbon. All it contains are hydrogens and carbons, all right? Non-polar, because it has some double bonds, but nothing like carbon-oxygen. So IR is typically not very useful, which is exactly what it is. So the bands you're going to explain are only this. It's approximately 2,900 wave numbers, to 3,000 wave numbers. Those are your carbon-hydrogen stretch. So the molecule is non-polar, so there is no major change in the dipole moment, so you don't see much of an information for anything except the carbon-hydrogen bonds. You do see a lot of carbon-hydrogen bonds in this molecule, and therefore this peak is strong, high intensity. It's high intensity not because the carbon-hydrogen bonds are polar, they're actually non-polar. It's high intensity because of the number of carbon-hydrogen bonds in the molecule. Sharp contrast in the previous problem, you see this carbon-oxygen is just two carbon-oxygen bonds, but a pretty strong peak. Strong peak means touching almost the x-axis. That's because of a great change in the dipole moment. Just two C double bond O's, but kind of a broad, clumsy peak, but still pretty strong. Here it's not because of the number of peaks, but it's because of the polarity of the peaks, and therefore a greater change in the dipole moment. Whereas in anthracene, the carbon-hydrogen bands are strong because you just got a lot of carbon-hydrogen bonds in the molecule. So those are your starting materials. Now we're going to look at the duct. Now, I couldn't find a better spectrum for the duct. I apologize, it's the best I could get. So I'm going to walk you through some of these bands because I kind of used a lens and looked at everything already. So it'll be easier for you. So we are looking at two bands here, and as unclear as this may be, but you just cannot miss look at that symmetric stretch. You do see that very nicely. And then you see another longer stretch. So we're going to identify all of them. We have three numbers there. And I'm going to give you those numbers here. So we're going to start with 1837 wave numbers and 1863 wave numbers. These are your carbonyl from the anhydrite. So one is for the symmetric stretch, the other is asymmetric stretch. You do not have to identify which one is symmetric, which one is asymmetric. That's beyond the scope. But I would like you to very much say that there are two bands, one for the symmetric stretch and the other for the asymmetric stretch, located at 1837 and 1863. Apart from that, the carbonyl gives its own stretching at 1779 wave numbers. That's just the carbonyl stretch, the true carbonyl stretch. Then we're going to go here. I'm going to point out a couple stretches here for you. One of them is 1231 wave numbers. You can kind of see that. The other is 1290 wave numbers. You have two carbon-oxygen bonds, right? You got one on this side and one on that side, left and right. So those are your two carbon-oxygen stretch in the fingerprint region. So right here, you see the other one. This is, I'm going to go with this number here, 3069 wave numbers. That's your carbon-hydrogen stretching. That's going to be there on all organic compounds. But we have identified the major anhydride peak. We have identified the carbonyl peak in the anhydride, you know, the symmetric and the asymmetric stretching of the anhydride. Apart from that, the carbonyl stretching itself has been identified. The two carbon-oxygen stretches in the fingerprint has been identified, okay? So you will explain all of this. There's no explanation other than stating the values and the stretches. I'm going to just pause here for a minute, and then I want to jump into lab flow and show you what you do there. So you got three spectra, okay? You can get a blank spectrum and write this nicely if you want. You can just, and then you're asked to upload some things, and I'll show you that as well.
Can you go to the second spectrum real quick, the one just above that one?
Anthracene?
Yes, thank you.
Do you want me to explain or just show it?
Just show it. Yeah, that's fine. Thank you.
Okay, no problem. Okay, I will come back to this, but what I want to show you is, so that then you have this question on the melting point range. For the crude product is 250 to 265. You're asked to predict the melting point range of the recrystallized product. This is a really broad range. Okay, so you want to just predict a narrower range. It's only a prediction, so don't worry too much. Equation for the reaction, you want to draw it on a piece of paper. If you click this, you should be able to upload the image. Post-lab questions. Here is your IR. Don't write one sentence saying, yes, the IR allows me to confirm the structure of the product. Take a look, it's 25 points. So you want to explain in detail the IR of maleic anhydride, anthracene, and all the important peaks, particularly in the final product. You want to do that here. You can just type that out. Over here, you can upload. This is where you will upload the IR spectra, the 3 IR spectra, and that completes it. Your lab report is 49 points, but it will convert it into 100, okay? So that completes this particular lab, and I will go back to this in case you needed to write something down. So let me know. That completes your first section of today's experiment, which is Diels-Alder. I do want to pause here and open up for any questions or anything that you may have, especially, lab flow should go no matter what browser, what computer you have, it should go a lot more smoothly than Labster. But then it's not a video game, it's not so interactive. Okay, so our next order of business here, that completes all the way to this. So you guys have finished the pre-lab. We've talked about the lab assignment. Now we will go to the UV-Vis PowerPoint. Similarly, I put together the UV-Vis PowerPoint, keeping the lab report in mind. There are 2 lab reports, as I mentioned. These 2 are the same PowerPoints, one PDF, one regular. Please do watch the Joe video on UV-Vis spectroscopy, because at the end of the day, science is hands-on. We are at a particular disadvantage. So see how, I will talk a little bit about how it is run, the experiment is run, but it's kind of nice to view that. Then we have a couple lab reports. We'll look at it together. The extra credit, you can do that on your own. So let us go to the UV PowerPoint here. So I've also shared this file both as a PowerPoint as well as PDF in the file share window, or you can get this from Canvas. So get this ready and then we'll get started. So again, a little bit of theory, but the PowerPoint is put together keeping the lab report in mind. What you see here is electromagnetic spectrum. So all the different energies that you see listed on the spectrum are affected by electrical field and magnetic field. So this is a spectrum that is very familiar to us. Starts with the gamma rays, X-rays, goes all the way to the radio waves. Your high energy is on this side. This is low energy. Keep in mind, higher the energy, higher is the frequency, lower is the wavelength. So wavelength and energy go opposite. So gamma rays are high energy. You can see the high frequency here. Frequency is the number of radiations per, number of waves per second. So you can see the low frequency here. So in 1 second, more waves are going to hit you, more gamma waves are going to hit your skin compared to radio waves. Plus, they have high energy. Okay. The wavelength here you can see is high. So this is high wavelength. Wavelength is defined as a distance between two identical points on a wave, on two consecutive waves. Whereas here you can see this is low wavelength. Wavelength is given by lambda. Frequency is given by nu. So again, no new information there, right? Now what we want to focus here today is ultraviolet visible. So you can see the visible is a really, really small portion of the electromagnetic radiation that excites the retina of our eyes. The ultraviolet is to the left of it. So the ultraviolet is higher in energy compared to the visible. Keep that in mind. So the wavelength for ultraviolet is lower, is smaller in number compared to the visible. So higher the wavelength, the light is going to move from ultraviolet to visible. That's an important concept. So this slide is really to show you the location of ultraviolet and visible, and for you to remember that ultraviolet is higher in energy, lower in wavelength compared to visible. The next slide is also very useful for today's lab. This shows the visible spectrum, which is made up of 6 colors, but Newton believed in numerology, so he introduced a 7th color, indigo. But it's violet to red, violet higher in energy compared to red. So here is your violet, so very close to the ultraviolet, and here's your red, very close to infrared. Okay. Now the actual numbers are here. You do not have to memorize, but we'd have to refer to these numbers today. This is your color wheel, which will also come in handy if you don't know the complementary colors. So here are the ranges of wavelengths for each color. And the color wheel shows you all the primary, secondary colors and the complementary colors. Let's say your object absorbs in the red. It absorbs all the red light. The complementary color, green, is what is emitted, and that's what your eyes will see. So if we can find what is the maximum wavelength of light an object absorbs, we can say what color it will emit. And so we know the color of the object, or we can predict the color of a given object, or we can confirm the color of an object. Okay. Here are some natural pigments. They all have colors, but that's not my goal here. But what I want to point out is the first thing you want to see here is extensive conjugation. I want to use the word extensive because you just don't have a couple of double bonds talking to each other. You have pi bonds that can move from place to place because of resonance. Apart from that, all these structures, except the last structure, which is beta carotene, that's the orange pigment in carrots, except that, all other structures have lone pairs. Lone pairs are also referred to as non-bonding pairs. You can see that if you have a lot of pi bonds and a lot of lone pairs, it turns out that these compounds are brightly colored in the visible region. So that's the big point I want to make here. More the conjugation, more the number of lone pairs, non-bonding pairs, the richer is the color, the greater is the chance that you're going to see the color of the object in the visible region. Doesn't mean the other regions of the electromagnetic spectrum don't have colors. The gamma radiation, they all have colors. We just can't see it. A retina of our eye can perceive that. That's something we are again going to use when we get to the lab report. You'll see that we are forming some relationship between conjugation and color. Our next slide adds to our knowledge from our lecture. This is somewhat new information, but not totally. Before we get to that, I want to start with something very simple, like a hydrogen molecule. A hydrogen atom has one electron, which is 1s. Another hydrogen atom comes close by. You know, they got to get to that van der Waals radius. Then one electron will simply, flip its spin, and that's when it'll form the bond. So when it forms a bond, you need a location where you can store these electrons, and these are called molecular orbitals. So the original orbital is an atomic orbital. So we got an atomic orbital from each hydrogen. So you got two atomic orbitals, 1 plus 1 will give you two orbitals. So one atomic orbital plus another atomic orbital, 1 plus 1 will give you two orbitals. But these orbitals are called molecular orbitals. There's one of a lower energy, and that's called the bonding molecular orbital given by sigma. The other one is a much higher energy. That is called the anti-bonding molecular orbital. So I'm going to say anti-bonding MO, and that's given the symbol sigma star. Whether it's atomic orbital or molecular orbital, the most number of electrons you can put in any orbital, the maximum occupancy is always 2. You got 2 electrons, you can put them both in the bonding orbital, and they're very happy because they're sitting in an orbital that's much lower in energy compared to the atomic orbitals. So they're really happy. They've come down in energy. So that's why hydrogen is a very stable molecule. Whereas a hydrogen atom is unstable. Because if it combines, it can bring the electrons to an orbital that's much lower in energy. I'm sure you've covered this at some point, okay? So as we expand this further, let's say we take helium, which is 1s2. It's going to bring its atomic orbital. They're going to combine 2 atomic orbitals, will give you 2 molecular orbitals, that is sigma. This is your sigma star. We got 4 electrons, but the maximum occupancy is only 2 in any orbital. 2 go there, 2 here. These 2 are super happy. These 2 are not. So helium says, yeah, out of 4 electrons, 2 are happy, the other is not. So I rather just not combine with another, helium atom. That's why just helium monoatomic is stable. This is not even known. This is unstable. So molecular orbital theory can clearly explain to us why bonding occurs and why certain types of bonds do not occur. Now we also have pi bonds. When we start getting into a little bit more complexity, we have pi bonds. And pi bonds also form orbitals. So those electrons in the pi bonds cannot sit in the sigma orbitals. They sit in pi and pi star, which is a bonding and anti-bonding. Then we also got lone pairs or non-bonding electrons, and those sit in what is called the non-bonding orbitals. Do we want to build a diagram now with all of these? No, we'll do that next week because we're going to get into some extensive MO theory next week and we'll build all these up. But what I want to show you here is just one simple thing. What is the order of arrangement of these orbitals with respect to energy? So which orbital Molecular orbital is what I'm talking about. Which one is really low in energy? Which one is high? The sigma bonding is always the least in energy. Sigma star is the highest. Then we got pi, and pi star right between is n. So that's the arrangement. If you calculate the energies of these orbitals, that's how they come out. Here are all your transitions. What that means is, let's say a molecule is hit by ultraviolet and visible light. It's going to have sigma electrons. Without sigma bonds, there are no molecules. All molecules contain sigma bonds. If there are pi bonds, you're going to have these pi bonding and pi star anti-bonding. If you got lone pairs, you're going to have these non-bonding orbitals, right? So depending on the makeup of this molecule, let's say you take a molecule which has sigma, pi, and non-bonding electrons, and you hit it with ultraviolet visible light. These are your major transitions, okay? Out of these, you can say that sigma star is the highest energy, requires the highest energy, followed by sigma to pi star. Approximately, I would say in the same level is a pi sigma star, right? Then comes n sigma star. I'm just arranging them in the order of energies. Pi star. The least is n pi star. Goes back to our basics. Delta E equals h nu, which is hc over lambda. Now this difference in energy, delta E, has to match exactly with the wavelength. Only then the wavelength will be absorbed. Otherwise, it will not be absorbed. So you're going to hit this molecule with wavelengths ranging from 200 nanometers to 800 nanometers. That should cover both the UV and the visible region. The molecule is not going to randomly absorb all wavelengths in that region. It's only going to absorb wavelengths corresponding to these transitions. It turns out sigma star is such a high energy, it doesn't fall in the UV vis region. Delta E is so high that we cannot find a lambda max that corresponds to that delta E. Similarly, you cannot find that. Okay, this one is rare, and we don't see much. So the two common transitions that we study are in blue, the blue arrows, n pi star and pi star. So those are the common transitions studied in the ultraviolet visible. So when you hit a molecule with ultraviolet light, electrons in the pi bond go to the pi star orbital. The non-bonding electrons jump to the pi star orbital. Those are your only transitions. Then they jump back down. Your detector detects energy and gives you the spectrum. So I'm going to pause here because that is new information. Please let me know if something is not clear. I can explain it again. Our attempt here is not to build these orbitals, but look at the relative energies of these orbitals and see what transitions actually occur when you hit it with ultraviolet visible light. Because in the lecture I said, you hit it with light, the electrons jump. That's all I said. And then they jump back. But I didn't tell you jump from where to where. Here I'm telling you that they jump from non-bonding orbital to pi star anti-bonding, from the pi bonding to the pi star anti-bonding. I'm telling you the beginning and the final location. Those energy differences fall exactly in the range of UV vis. So there will be wavelengths of light that match the n pi star and the pi star. Those wavelengths will be absorbed. There'll be more than one, but those will be absorbed. The one that's absorbed the most is called lambda max. This is the wavelength of maximum absorption. This is what is really interesting to us. This is the wavelength that is most absorbed. So this given in nanometers. And this picture here shows you three different molecules, green, pink, and blue. The green molecule has 3 pi bonds. The pink molecule has 4 pi bonds. The blue one has 5. So n equals 3. Then we got 4 and 5. We have less conjugation, less resonance because you got less pi bonds, more conjugation. You just got more resonance. So this is what I see from the graph. Greater the conjugation, I know, lower the energy, higher the lambda max. See how the lambda is moving from 200 to 380? So more number of conjugated double bonds, the energy drops, the lambda max will increase. So lambda max will move from UV to visible when conjugation increases, when number of double bonds increase. So if you take a compound with 5 double bonds, the lambda max will be much higher compared to a compound with 3 double bonds. So I want to just quickly stroll back to these molecules. This is the connection I was saying. The more double bonds, the more lone pairs you have, greater is the resonance, greater is the conjugation, more is the stability, higher is the lambda max. So that's an important aspect of today's lab that you will be, studying. So let me know any questions there. This is something we did learn in the lecture, but here we are looking at a graph to understand it further. Now, the onset, this looks confusing, so I'm going to take this stepwise. So we're going to start with this first one here, which is C double bond C. So it's a simple molecule with just one double bond. So it has one double bond and therefore has one pi and one pi star. This is your bonding. This is your anti-bonding. You hit this molecule with one double bond with light, what happens is one electron jumps from pi to pi star. Now, this orbital is called HOMO, stands for highest occupied molecular orbital. This stands for LUMO. The pi star is LUMO. This is the lowest unoccupied molecular orbital. The transition occurs from HOMO to LUMO, always, no exceptions. There's only one HOMO, there's only one LUMO, that's because it's a simple molecule. So you got to transition from HOMO to LUMO. Let's go to the bottom where we have two double bonds. You have two double bonds, so you got pi 1 and pi 2. Those are the bonding. Pi star 3 and pi star 4. The star indicates the anti-bonding, which is higher in energy. This is my HOMO, highest occupied molecular orbital. This is my LUMO. I hit it with light. It's always HOMO to LUMO. So an electron from pi 2 goes to pi 3. No other transition will take place. So now we will increase the number of bonds to 3. So we got pi 1, pi 2, pi 3, all bonding. The stars are all anti-bonding. This is my HOMO, highest occupied. This is my LUMO. I hit it with light. An electron jumps always from HOMO to LUMO. No exceptions. So this is another piece of extra information that you're learning when you hit a compound, when ultraviolet light and visible light is incident on a compound, the transition occurs between HOMO and to LUMO. Now we'll get all three graphs here and look at something. This gap is called the HOMO-LUMO gap. This is your HOMO-LUMO energy gap. Kind of see that distance of the length of the arrow. This is your HOMO-LUMO gap. It's getting smaller. Look at this HOMO-LUMO gap, even smaller. So as the number of double bonds increase, or as the conjugation increases, the difference between the HOMO-LUMO gap decreases. So smaller delta E means higher lambda max. So what does conjugation do? All along we've been saying that if you increase the number of double bonds, the energy of the molecule drops, so lambda max increases. We're giving a more refined answer using molecular orbital theory. We're saying as you increase the number of double bonds, the HOMO-LUMO gap decreases. Smaller the gap, the easier the jump Smaller the delta E, higher is the wavelength, okay? So that's the theory of UV vis. In addition to what you learned in the lecture, will give you everything that you need for 236 course competencies, okay? So before I get into just the experimental part, any questions with any of these? The molecular orbital theory is quite challenging. We'll get into more of it next week. Anything you would like me to explain more, please let me know. Okay, let's look at what is a UV vis spectrometer. Its makeup is very simple. You have a source that gives out visible light. A lot of compounds can give out visible light. That's white light. And if you send it to a prism, it can break it into all the colors. But if you want to get the ultraviolet light, you need a special lamp, and that is the deuterium lamp. The deuterium lamp gives out ultraviolet light. So a lot of times we have a source for UV and vis, both kinds of light. It comes through a slit, so you get a narrow beam of light. You have mirrors that focus. It's called a double beam because you're going to get two beams of UV vis light. Here is beam 1 and here is beam 2. And you have the sample in what is called a cuvette. So the sample, whether it's a solid or liquid, must be dissolved in a solvent. If you use a solvent like hexanes, all it has is sigma bonds. There won't be any interference. If you use water, there are lone pairs, there will be interference because those electrons, those lone pair electrons in water can also absorb UV light and jump. If you use something like benzene as your solvent, benzene has pi bonds. So your reference is always a blank, and the blank is nothing but a solvent. So you also take the UV spectrum of the solvent. You also take it for your sample dissolved in your solvent. Your computer will subtract the solvent spectrum from your sample and give you only the sample spectrum. So that's the advantage of a double beam. If you have a single beam, you have to do the solvent first, and then you have to do the sample, and then you have to ask the computer to subtract. If you have a double beam, which is what we have in our lab, you can just stick in the solvent cuvette and your sample cuvette. It takes about 30 seconds or so to get the spectrum. Information that you'll get from the UV vis is lambda max. So you're working in research and you get a lambda max, you can work backwards. Working backwards, you can even say that this lambda max, you have so much of conjugation, which means you have so many double bonds, so many of them are in resonance, you can even predict. So it gives a lot of idea about the structures of the molecules in that regard, but you don't get any other information from the UV vis. This is all that you get. So it's not as powerful as the infrared NMR that give you the complete structure of the molecule, but it does tell you a lot about conjugation. Limitations of UV vis, your sample must be completely soluble in the solvent. So if it's not completely soluble, you have a slurry or you have like particles moving around. What happens is UV light hits the cuvette. Some of it is absorbed, some of it is transmitted. So this is your incident light. This is your transmitted light. And of course, some of it is absorbed. Okay, 100% incident, you're not going to get 100% transmittance. Some of it will be absorbed. But what you don't want is this. I'm going to draw a bigger cuvette. You have some particles here floating around. Light start getting scattered and gets caught in the sample and just, doesn't come out. Not enough comes out. There's a lot of, bending of light and diffraction and, scattering of light. So you really need a very clear solution. By clear, I'm not saying it should be colorless. Colored is certainly allowed, but it should be clear. Okay. So all of these points will come in very handy when we look at the lab reports. So please let me know if you have any questions before I go to the lab reports. Anything at all. You'll see we will be reviewing this. We'll be connecting to these concepts when we answer questions. Okay, so what I'm going to do is the next one I'm going to look is UV vis food dyes. That's what I want you to look at. That's going to open as a PDF. It's going to look like this. This gives you the theory again. You can read that on your own. It tells you what the method is. It's something we do in the lab. You'll take different food dyes. You'll make solutions. And this is something that I've already given you. Those are the color ranges, your UV vis. Keep in mind, you know, your UV can start from 100 nanometers, but we don't really study from that. We go from 200 to 400 is our UV. Then keep in mind 400 nanometers to 800 nanometers is your visible. So if your substance absorbs in blue, the complementary color is what you'll see. This is important. Okay, we'll come back to this a bit, quite a bit. So these are your different color dyes. You're going to write down the actual absorbance and notes. So in the lab, you would have taken all these colored dyes and you would have obtained these spectra. But now these spectra are given to you. All right. So let's start with them. The red. Well, the numbers that you see here are the theoretical. The number you see on top of this graph is the actual absorbance value. That's what you as a student got in the class. You should have seen one at 528, you didn't. That's okay, so you see 519. So what you're going to do here is write 519 wave numbers. So that is the maximum light of that is the light, you know, that wavelength 519 is what is most absorbed by the compound. Now in the notes, what we're going to do is we're going to go back here. We're going to locate where 519 is. So if you take a look at it, it is in the green region. So this compound is absorbing all the green light. What's emitted is the complementary, which is red. That's why you see it as red. So in the notes, you're going to say, like this food dye absorbs in the green region of the visible spectrum, okay? The complementary color red seen, or you can say emitted. So this is how you're going to fill out the rest of it. You do see a strange one there, black. So we'll look at that. But before that, any questions? So it's pretty straightforward. The one thing you want to remember is that's theoretical. Your actual will be right on top of every spectrum. Sometimes you may have two. So what you have to do is you can take a look. This is approximately 0.6. That's a little above 0.6. So it's very hard to say, you know, both of them. So you have a lambda max 1 and a lambda max 2. So you have two wavelengths, you know, of equal absorption. You're expected to be 635. That's your theoretical. But for green, you're going to write both 426 and 632. And you'll see something interesting. Let's do that. 426, 632. And then if you go back here, so this is the one for green dye that we see. So the 426 comes in the violet region, and the 632 comes in the red region. So what we're going to see is it's absorbing in the violet region and the red region. So it's going to give out yellow and green. So it's not a true green. This green is going to be a yellow green. Now, is it yellowish green or greenish yellow? I'm not able to find that out. simply because these both are, approximately the same absorbance. If one was absorbed a little bit more than the other, then I can say that corresponding complementary is a more dominant color. But at this point, I cannot say whether it's yellowish green or greenish yellow, but it's a yellow green. It's not a true green. Okay. When we get to black, it's 519 and 635. So we see 517 and 634. So go ahead and find the colors here. For 517, it'll be green. And then for 634, it is red. Just erasing these because I'm recording it. You should be able to see all of this again. So it's absorbing green, it's absorbing red, it's absorbing the complementary colors, and that's why it comes out as black. So on a paint palette, if you mix green and red, you'll get brown. Typically, that's what you get. That's because you really don't have the primary green and the primary red. If you have the true primary red and green and you mix it, it'll probably be black. But we usually don't have those. Primaries are hard to obtain. So we mix any red or green, we get a brown. But the complementaries mix, that's when you get black. So that's how you'll fill it, and that's all there is to this particular part of that lab, okay? So let me know if you have any questions here. I don't have any other comments to make about this lab report. So you will complete all of this, and that's it. Okay, the next thing we want to do is actually I'll go into the student view. I'm going to open the next one, which says UV-Vis spectroscopy LRA. That's your lab report assignment. It works better in the student view for me to type some things out, and we will look at that. What time? We are not coming back, Kelsey, unless you want to come back. I'm just going to give you everything. I'm almost at the end of this. I know you guys are tired. I'll skip you for a little bit more time. This is the last piece for the ultraviolet vis, and then I'll talk a little bit about Spartan, and then we are done. And then you don't have to come back, but what I did for Monday is I stayed logged on till 3:30, and some students jumped back into the WebEx call, and if you want to ask questions, that's cool. You can do that. But you don't necessarily have to come back. So let me go into this lab report assignment. Making this, just kind of walking you through the PowerPoint presentation should really help you because I put it together based on the questions here. Okay, so that familiar drawing is right here. You can see that we talked about, and then we have some questions. So we'll go ahead and answer a couple of them, and it's pretty much I've given you all the answers in the pre-lab itself, but let's take a look. Which jump needs the highest energy? So what do you think is the longest jump here? Highest jump? Sigma to sigma star, very good. That is the highest energy. So which jump absorbs light of the highest frequency? Keep in mind, higher the energy, higher the frequency. So the highest frequency will also be sigma, sigma star. Keep in mind, higher the energy, higher the frequency, lower the wavelength, okay? And then the three longest jumps are not going to be useful in the UV-Vis spectroscopy. You should know how to explain that. If the energy difference between the two orbitals or the energy difference for the jump does not fall or does not match with any of the wavelengths in the ultraviolet visible region, then it cannot be studied by that spectroscopic tool. Okay? So this delta E of sigma, sigma star should match with any of the wavelengths in the UV-Vis region, which is 200 to 800 nanometers. But if it doesn't, energy is so high, the wavelength is smaller than 200 nanometers, you cannot study using ultraviolet visible spectroscopy. So those, take a quick look and let me know if you have any questions, but those should flow pretty okay, I think. As long as you keep in mind the relationship that higher the energy, higher the frequency, lower the wavelength. So let's take a look at the second question. We have three, conjugated compounds. One is not conjugated, that's ethene, that's only one double bond. Then we got a conjugated diene, buta-1,3-diene, and then the hexatriene. So you have more conjugation in the triene, higher the conjugation, lower the energy, greater the lambda max, which is what you see. So the 171 to 258 is an expected trend. The greens are all bonding orbitals, the reds are all anti-bonding orbitals. So the first question, why are there more of each as you go from butadiene to 135 triene? So you only have 2 orbitals in ethene, but you got 6 in hexa 135 triene. Why is that? So when you go back and look at the structure, how many pi electrons do you have in ethene? Only 2. How many do you have in the diene? I'm only talking about pi electrons, not all electrons. You got 1 pi bond here, you got 2 electrons, you got another pi bond here, 2 more electrons, so that's a total of 4. You got 3 pi bonds, so you got 6. So more number of electrons requires more orbitals for placement. That's why the orbitals increase from ethene to triene. So as the number of pi electrons increase, the number of pi orbitals increase to occupy these electrons. So that will be your first question. Is everyone okay with that? So you got more pi bonds, you got more pi electrons, and therefore you need more orbitals. You cannot fit in 6 electrons in 2 orbitals. You can only fit in 4, right? So you just need more orbitals. And for every bonding orbital, every green line, you will have a red line. There will be an anti-bonding. The next question is relationship between these diagrams and the lambda max values. So I want you to look at these black arrows. Now my pointer is pointing to the HOMO. This green line here is the highest occupied molecular orbital, HOMO. This is LUMO, lowest unoccupied molecular orbital. The electron jumps from HOMO to LUMO right there. This is your HOMO. In diene, I'm pointing to the HOMO, that's LUMO. The arrow is much smaller. This is HOMO, this is LUMO, arrow is much smaller. So we're going to relate this drawing to these wavelengths. So we can say that as we move from ethene to the triene, the HOMO-LUMO gap decreases. So you can say the HOMO-LUMO energy gap decreases. The jumps do not require, I would say something like the energy required for the jumps decreases. Right? The energy required for the electrons to jump decreases because the gap decreases. This increases. So once, the energy decreases, this increases the wavelength, which is the lambda max. So what we have done is the first part is the HOMO-LUMO energy gap. We're talking about that. That's the diagram. And then we're relating it to the wavelength and we're answering this question. Okay. Questions? Yes, please.
So the smaller the wavelength, the more conjugation, the higher the energy.
Okay, can you please repeat that? Can you please repeat that?
So the lower the wavelengths, like for that third one, the hexa 135 triene, So smaller the wavelengths, the higher.
The 258 is higher wavelength. 258 is higher than 171.
Okay, so higher the wavelength, the more conjugation, the more energy.
Less energy. You see how small that gap is compared to this gap?
Okay. Okay, I knew I was missing something.
So that's your HOMO-LUMO gap. More conjugation in the triene. That means this gap reduces, the wavelength increases.
Okay. Thank you.
Sure. Anything else, guys? Let me know. So we got the beta carotene structure. This is the main pigment of the carrots that imports the color to carrots. I have highlighted the double bonds in red. What's interesting, you see how the conjugation goes from within the ring all the way from one ring to the other ring. It's just not these double bonds, even the double bonds in the ring that are delocalized and involved in resonance, okay? So this one absorbs, has many absorptions, ranging between 400 and 500 nanometers, all of them in the visible region. The maximum absorption, the light that it absorbs the most is 470. So 470 falls under blue. So if you go back and look at the color wheel, if a substance absorbs in blue, the complementary color is orange. That's why carrots are orange. So that's all you're going to explain. Okay. So hopefully you understand the sentence that it absorbs a lot of different wavelengths, but the wavelength that it absorbs the most is 470. That's the lambda max. That falls in the blue, the complementary color is orange. Now, the next question, I'm going to copy down that magenta form, and you may want to do that too. And then I'll talk to you. Then we'll read the question together and we'll talk about this. So I'm copying the structure on the right. And as you copy it, go ahead and put the lone pairs of the oxygen. We need those. Okay, so phenolphthalein, a very familiar compound to you guys coming from Gen Chem. It's an acid-base indicator. It's colorless in acid medium, and you know your endpoint is pretty dramatic. With one drop, you get a bright pink color. Okay, so this particular compound is colorless in acid medium, but in the base medium, it takes on a very bright color. So when there's sufficient amount of base, what happens is the base comes, now you know more chemistry. It can pull out the hydrogen from these alcohols and make them O minus, and then it takes on this form. Okay, and there's a little bit of reaction as well. So we're going to explain why the colorless forms becomes magenta. By now we know that, you know, it's moving from probably ultraviolet, where I couldn't see the color of it. My eyes couldn't see the color in the ultraviolet region, or even further beyond. It's moved to the visible region because I'm seeing the pink color. We want to explain why my eyes can see the color of this, but not that. Okay, so what we are going to do is, I'll just leave the student view here. And, to my thing, this is where I want to be. Okay, I copied that structure and I put all the lone pairs on the oxygen, almost all of them. And now we will look at the conjugation. Okay, so I'm going to start with a color here, and I can see I can push this lone pair here. This has got to have more conjugation than the other one. I'm trying to show the extensive conjugation that can occur. So that's one arrow. So let's try another one. Then I'm going to push it on this side. My green is the other one. So there are many different ways I can push the electrons. Then let's look at this one here. There's conjugation there. Okay, let's look at another one. So I have the pink, the green, the purple, and the red. Those are all different ways the electrons can move. So what we have is, the key word is extensive delocalization. Greater the conjugation, smaller the HOMO-LUMO gap. You can go that way. That'll be a molecular orbital explanation. Okay, so higher is the lambda max. So from colorless, it moves to the visible region, and that's why you can see the color. If you don't want to use molecular orbital theory, you can go something like this: extensive or more conjugation, which is the same as delocalization. Lower is the energy of the molecule, which is not a great explanation, but it works. Higher is the lambda max, same idea after that. This always is a better explanation because you're going deep into the electronic level and you're explaining it. Now it moves from the colorless to the visible region, and so you can see the color. Either way, you're talking about conjugation. You see that? And you're comparing the conjugation to the energy. In the right side explanation, you're just saying the energy of the entire molecule drops. But on the left side, you're saying that more delocalization, the HOMO-LUMO gap decreases. So it doesn't require much energy to jump, which means the wavelength of the light that's absorbed is much higher. I'd say in any day, the molecular orbital theory is always more respected. It's a better explanation. But if you absolutely hate it today, you want to go with the right side one. It'll take some time to like it. We'll look more at it next class. So you definitely, I don't expect you to draw every single conjugation separately. I didn't do it either. You don't have to show all the resonance structures. But if you show that the possibility of conjugation is a lot more for this molecule in the alkaline form, that's good enough. So you may want to draw this, take a picture, and upload it. That should bring us, I believe, to the end of this UV-Vis spectroscopy. Just bear with me for a few more minutes. And I did this pattern a little bit differently this time, and it seems to be helping the Monday section based on the feedback I'm getting so far. So you should be okay, I think. Any questions on this? So you got to have a logical push of these electrons. Take a picture, write this down, take a picture, whatever works for you, okay? So what I want to do now is go into this courses. Okay, I'm going to turn off the sharing window here, and then I want to look at, so I'm going to leave you do this on your own, which is the Joe, and the extra credit is up to you. Now, when you go to Spartan lesson 1, I did this a little bit differently and hoping, so you're going to select this and you should see everything. You should see the written instructions. I worked this entire thing out, so you should see the video instructions. You should see the Spartan file. You should see the template and the PDF. Okay, so all of this should be pretty clear as you go through this. So we are looking at conjugated dienes. So let me just jump over here. So this is what I've done, and hoping this will help. So what I did was I built 1,3-butadiene I believe I built a 2,3-dimethyl-1,3-butadiene as well. But anyway, you do have at least one of the, this definitely there. I've shown you how to build it, how to run the entire calculation and whatnot. I'm asking you to do this, and this structure is incorrect. So go ahead and write the correct structure. It is 2, 3, 4, 5. You will not be able to build this molecule. So when you get home and try this, this could turn out to be frustrating. So I sent an email to the Monday section. I'm yet to send an email to you guys. This is what you're going to build. And I'm going to give you the structure as well. So this hexadiene, at 2, you have a double bond. You have a methyl group, 3. So this is your 1, 2, 3. Then at 4, you have a double bond again. This is your 5 and 6. So this is a structure you want to build. You'll not be able to build 2, 2, 3, 4, 5, 5 hexamethyl, but you will be able to build a 2, 3, 4, 5 tetramethyl 2, 4 hexadiene. That's the one you'll be able to build. So please write that. You're going to build that. I'm showing you exactly in that video clipping how to build a cis and how to build a trans. So you should be able to do that for both these molecules. And then I've also shown you how to get the energies. You'll just follow the same instructions. But apart from that, I also have the written instructions in case you like that. But I think most students will select the video and watch it. And I've given you the energy values for the cis and trans conformations of 1,3-butadiene. That should be a Spartan file. To be on the safe side, I will email this to you. That's what I did to the Monday section. I will send you the Spartan files as attachments to an email because sometimes Canvas struggles to open it or download it. So I will send that to you. I've done something similar for lesson 2. So let's go back to lesson 2. So if you select this, again, you should see written instructions. You should see video instructions. You should see the answer templates and the sample file. I will email this file. So I'll be emailing 2 data files just in case you cannot open this. You should be able to see the data. Okay. With that, I think you should be able to finish it. So with this, I'm going to stop. If you have any questions, you can check with me. I'm going to stay logged in until 3:30. I just want to point out that I'll be working on a different screen. So don't type something for me because I'll never see it. So please unmute and talk to me. That'll really help. Then I'll come on to your screen and I will help you. But otherwise, we are done. You do not have to return. Okay. So thank you and have a nice day. I will go ahead and stop the recording, process it, and send it to you.
I did have